So in this particular session, let us try to understand something very important thing, which is our Zynq SoC architecture. Okay, and our Zybo board is going to have this Zynq FPGA. Right? So let us try to understand this Zynq FPGA architecture in more detail. What do you mean by this Zynq FPGA architecture? So before that, as you know already, we are KT Semicon is launching a new batch where the courses are design and verification, physical design, and embedded systems. And as you know, you can also write down the scholarship test so that you can get some coupons, or if your performance is too good, then you might get 90% to 80% fee reimbursement in this particular course. Okay, so it is both in online and offline, right? Yes. So coming back to our course, let us try to understand about this Zynq SoC architecture, right? Now, this particular Zynq SoC architecture, it's as I've told you, the processor is basically present on a single chip. Okay, so the processor is basically present on a single chip, and the processor is hard coded processor. So we have classified our FPGAs into three types, right? So the FPGAs with no processor at all, and the FPGA with soft processor, and FPGA with hardcore processor, which is present in it, right? So this is the third category which we are going to have. Okay. Now this particular Zynq SoC combines two powerful domains: the processing system (PS), the gray color shade which you can able to see over in the upper region, right? This is nothing but my processing system. This is my hardcore processor, which is actually fabricated, right? And and the programmable logic, that is nothing but my PL. The yellow color thing you can see, right? This is nothing but my programmable logic. That is nothing but my PL. Um, so whatever the code you have written, right, that is going to be implemented over here. The Verilog code which you have written will be actually implemented on this FPGA, right, or the programmable logic, which is basically shaded in the yellow region. Okay. Now, this basically the hybrid architecture enables both software flexibility and hardware acceleration on a single chip. Okay. Now, the processing system features dual ARM Cortex A9. So this processing system is going to have, I think it's visible. You can see we are going to have a dual ARM Cortex A9 processor with peripheral supports which we are going to have, and the PL, that is nothing but my programmable logic, which is going to have FPGA fabric for custom hardware implementation. Okay, so we have seen, right, we can basically program our FPGA whatever the way we want, right? So that is the customness this FPGA is giving us. Okay, so together these are creating a versatile platform for embedded systems development. Okay, so this is nothing but my Zynq SoC architecture. And 1 minute. So this processing system, if you carefully observe, we have something known as SPI, I2C, CAN, UART, GPIO, SDIO, and USB, gig DMA. Okay, and I have something known as processor IO ports, and I have here EMIO. Okay, yesterday someone has asked, right? That is what we are going to see over here, and you can see general purpose AXI ports. Okay, so if your processor wants to communicate with this FPGA part, you are going to use this AMBA AXA protocol. Okay, you're basically going to use this AMBA AXA protocol for establishing the connection between this processing system and the FPGA. Okay, so for establishing the connection between this processing system and the FPGA, here you can see we have something known as general purpose AXA ports. Okay, and here also you can see high performance AXA ports. Why we need this, we will discuss. Okay, and we have something known as AMBA interconnect for basically establishing the connection between these two parts. Okay, and we have multi-channel gigabit transceivers, and this and all we will discuss. Okay, so this is nothing but my Zynq SoC architecture. Now, what are all the things which are going to be present inside my processing system is, one is my main processor, which is ARM Cortex A9 MP core. So which is a dual core processor with 32 KB and caches, and these are all the specifications which is going to have. Okay, and it is also going to have the memory controllers for controlling your DRAM, DDR3, DDRL, DDR low power, DDR2 plus flash controller. It may be NOR flash, NAND flash, SRAM flash, or Quad SPA. Okay, So all the memory controllers will be present inside your processing system only. And peripheral IOs also. So it is going to have all the peripheral IOs for SPI, I2C, CAN, UART, okay? And it is going to have security and debug like advanced encryption standard, SHA, RSA encryptions, okay? And these are all the features of my processing system. And here the important point that is to be noted over here is it is going to have something known as peripheral IOs. Okay, so let's say this is nothing but my processor and this is nothing but my PL. Let us come back to PL later, but we are going to focus upon this PS. Why I'm going to focus upon this PS is so this PS is going to have this controllers. So these are all my controllers: UART, GPIO, SDIO. These are all my IPs which are present. Let me show you. So this is nothing but my programming system PS. So all the logic. So let us take one particular IP like UART. Okay. Now let's say if I want to have a particular if I want to establish a connection of using my UART. Okay. So let's say if my data has been sent and if I want to send the data using this UART, okay, UART protocol, then my processor is going to take care of that particular thing, how it is going to use this UART IP. Now what it is going to do is it is going to create the UART frame, and it is going to create the baud rate. It is also going to set the baud rate, and it is going to send the data serially to actually speaking my USB. Okay, so there will be something known as UART to USB converter, and from USB I am going to get my data out. Okay, let us take one example. It will be more clear. Let me share one screen. Yes. So where is this? Exactly this one. So you can see over here, there is something known as my USB interface. Okay. So if you carefully observe, yesterday also I have connected my system with my with the cable using this USB interface, right? So let's say from my system, if I want to send any data to my processor, okay. So what I'm going to do is I'm going to send that particular data to this particular USB interface, and let's say if I want to receive that particular data to my processor, okay. So that particular there will be something known as USB to UART converter, okay, and that particular data will be converted into UART format and it will be sent to my processor. Okay, so I have my processor over here, right? So my processor is going to have something known as UART controller, which is going to receive that particular UART frame, and it can also filter that particular UART frame. Okay, so whatever the data you want to receive via the UART, or the whatever the data you are going to receive via the UART frames, it can basically receive those, and it can basically understand those. Okay, so my processor has that particular capability using this UART interface. Let's say if I'm going to get the data in the CAN protocol format, then also my processor is going to have this CAN IP, which can actually process my CAN data. And let's say if I'm going to get the data in I2C format, then also my processor is going to have this I2C controller, which can actually understand that particular thing and which can filter that. Okay. And let's say if I'm going to get the data in SPI format, then also it can understand it, and it can basically debug it. Okay, so this processor have all this particular IPs which are present inside it, so that it can process those particular data whenever we are going to have. So is it clear for everyone? Are you able to follow me? Is it clear? Great. Okay. And the very important point over here is I'm stressing on this particular point: processor. Processor only is having a direct connection with this particular controllers or the IPs which I have shown you. Okay. So from the external interface which I'm going to send, this only these processors are going to have this particular control over the processor is going to have the control over this IPs. This FPGA is not having a direct connection with this IPs. Okay, this is a very important point to be noted over here. This FPGA is not having any direct connection with this particular IPs which I am showing you, like SPI, I2C, CAN. Only this processor is going to have a direct connection. This is a very important point. Now, you might get a doubt over here. Let's say, suppose from our RTL code, if my FPGA wants to have a direct connection with this particular processor, then how? Then what are we going to do? That is what we are going to discuss later. Okay, that is what we are going to discuss later. We will discuss this later. But now, what are we going to understand is we are going to understand how this processor is going to communicate with this particular controllers or the IPs which we are going to have, right? Yeah. So that is what I was talking about on-chip peripheral protocols. So the peripheral controllers are physically implemented on the silicon, like your UART IP or the SPA IP, all are physically implemented on the silicon in the processor side. So just like ALU and the cache, and these hardware IPs are not written in Verilog by the users. This hardware IPs which I have shown you, these are all not FPGA side or which are implemented using the LUTs. These are actually implemented on the silicon chip. Okay. Now, these are pre-built hardwired component integrated into the SoC. So each peripherals includes control registers, status registers, data registers mapped into the processor's memory. Okay. So we are going to use the software language like C language or C++ for interacting with this particular peripherals. For example, if I want to communicate with a UART IP, okay. If I want to communicate with an UART IP, then I cannot directly establish the connection from my FPGA side to this UART IP. What I need to do is I need to develop a application in C from this processor side, and the software which we are going to use is Vitis. Okay, so using this Vitis, we are going to we are going to develop a application using this C. Okay, so using this language C language, we are going to communicate with this particular UART IP. Now, if I want to communicate with this particular UART IP, this IP is going to have some set of registers and all. Okay. So if someone has worked on this particular things, they might be familiar with this, but no issue. Okay. So this particular IP is going to have some registers like control register, status register, and data register. Now, if you want to access any particular register, you need to provide that particular address, and then only you can access that particular register. Let's say suppose this IP is going to have three number of registers like this. Now if you want to communicate with this particular register which is present over in this particular IP, then in the software level you need to access those particular you need to provide that particular address so that you can establish that particular communication. In the software level you need to provide this address so that you can establish the connection from the processor side to this IP which you want to use. Okay, not from the FPGA side. So this is how you're going to establish the connection between this whatever the IPs you are going to have with your processor. Yes, it's an intellectual property. IP is an intellectual property. Okay. So there are basically two type of IPs. One is hardware IPs and soft IPs. Hard IPs are basically this. This is the example of your hard IP, and soft IPs are basically your codes which are implemented using the software. Okay. Yeah. So let me explain it one more time. The agenda is very simple. If you want to have a communication between your processor and this particular IP, you are going to use another tool, not Vivado. You are going to use another tool which is known as Vitis. Okay. So normally embedded people are going to have this particular. They are going to use this particular things. Okay, or you can say your embedded developers or they are going to have this particular type of things. They are going to develop the drivers and all these particular things. Okay, so they are going to use this particular software which is known as Vitis, where they are going to develop a application using the C language or C++, and they are going to communicate with this particular IPs. Now how they are going to communicate with this IPs is each IP is going to have some set of registers. Okay, now, what is this registers is nothing but these registers are used for configurability. Okay. Now, if you want to access this particular register, you need to provide that particular address corresponding to that register. And if you want to communicate with this second register, you need to provide this address for the second register. Okay, so if you provide the base address plus this offset address, you are going to communicate with the control register, and base plus offset address you are going to communicate with the status register. Like this you are going to establish the connection between the processing system and this registers. Okay. Now, next comes the UART hardware versus software. So, in the hardware controller, which we have seen over here, these are basically the UART controller is a hardware peripheral inside the SoC. That is what we have seen, and it's not a separate IC. It's not a separate IC. This is basically embedded inside your processor itself. Okay. Now, it includes the shift registers, baud rate generator, TX, RX logic, and interrupt handling, and all the implemented in the silicon itself. And the controller, and whatever the controller which we have seen, the job of it is to convert the parallel data to the serial format, generate start and stop bits, sample RX data at the correct baud rate, and raises interrupts when the data is delivered or TX buffer is empty. Okay, so if you have studied UART protocol, this will be familiar to you. But if you are new to UART protocol, then no worries. This will be completely new for you. Okay, it is just following some protocol related stuff that will be taken care by the UART controller. And from software or the driver, embedded people are basically going to develop something known as drivers, and they are going to develop those driver applications. And what is the driver is going to do is it is basically running on the ARM Cortex in processor, and it is going to configure the hardware by writing memory mapped registers. Just now I've shown you, right? So these are nothing but my memory mapped registers. If I want to write down any data to that, I'm going to use this addresses. Okay. And what is the driver responsibility? The responsibility is to include the baud rate or enabling the TXRX or managing the interrupts or for sending the commands like send the data or receive the data from the application level itself. Okay. So let's say this is your processor, and above this processor you are going to write down a software application. Okay, so you are going to write down a software application. This application is going to control your IPs which are present inside your processor. That is what they are going to do. Okay, yes. So is it clear for everyone? Any doubts or any queries? So we have something known as external UART hardware. So most development boards don't have a separate UART IC. So they are going to include the external components for converting the signals, but they are not going to implement the UART itself. So that is what we have seen, right? So we are going to have something known as USB to UART converter. So here there will be some particular chip which is going to convert your USB to UART. I don't find that particular IC over here. Basically, that is going to convert your UART signals from the processor to the USB signals. It is going to convert it. Okay. Or we are going to have something known as level shifter or the physical connector like your RS232 for PC communication. Okay. So this is how you're basically you're going to control your IPs which are present in your processor set. Okay, so this is the flowchart. The application code will be present, and in that we are going to develop a driver, and the driver is going to control your UART controller. Now, UART controller, if it needs to communicate with the outside chip environment, we are going to have something known as EMIOS. Okay, so we are going to have the EMIOS or MIOS, which we are going to use. The controller is going to use. Okay. Now, what is this MIOS is nothing but it is a direct connection from the PS peripheral to the physical pin, offers faster communication and lower latency. For example, this is nothing but my processor which I'm going to have. This processor is going to have several multiplexed input output ports. MIO means multiplexed input output ports. Okay. Now, if this processor is going to use this MIOs for connecting or for establishing the connection with the outside environment of the chip. Okay, using this MIOs, I will show you in the data sheet. Also, we will have something known as MIOs. I think yesterday, if someone has observed that, okay, I will show you again where is this exactly present. And we have something known as EMIOS also, which is nothing but my extended MIOS. So where the signal routed through the programmable logic before reaching the pins and use it when extra pins are needed or custom logic is required between the PS and external world. For example, in the diagram you can see over here, EMIO is basically having the connection with your FPGA. So if you want to establish a connection with your outside of your chip from the FPGA side, you can use this EMIO pins. Okay. Yeah. So this is how you're going to control your processor side. Yeah. This is what I was. Okay. This is a different one. Yeah. So this is how you're going to control your UART IPs or I2C IPs or SPI IPs or whatever the IPs which are present inside your processor using the application code which is going to be written in your C language or C++, and the tool which you are going to use is Vitis. Okay. Yeah. So in our tomorrow sessions, we are going to see about what is this pmod and why we are going to use this pmod and how this pmod is going to work and where is the connection from this pmod and where to find the connections in the data sheet and where to find the connections of this MIO and EMIOs in a data sheet. Okay. So this is what we are going to see in our tomorrow session. Yes. So that's about this particular session. Thank you.